think that, but we're back live. Or because isn't that what everyone wants to do? Or at least that's the plan. But today, what we're going to be talking about, this was inspired by, oh my God, I forget his Garrett. No, Garrett. Garrett. Let me just check my audio right now and make sure I'm actually transmitting. Yes. Let me just check my audio right now and make sure I'm actually. Okay, I sound choppy. I'm going to swap my audio out. Give me one moment here. We'll be right back. Time to get new headphones.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Rulliad. I don't think it rules them all, and it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Test. 1, 2, 3, 4. Let's see how it actually works out now. Okay, that's much better. All right, there we go. It says it works. I mean, whatever. All right. So today we're going to be talking about something that was brought up by one of the gentlemen that was one of the speakers at the Mysticon 2025. So let's bring it up right now, and this is from Gareth. I spent the entire weekend calling him Garrett. I apologize, Gareth, but I'm terrible with names. Okay. So here's what we got. So let's go back here. As we can see, I totally stole my thumbnail from Gareth here, as we can see here. Basically, I just did this, and then I superimposed the simple Ampere thing. Why? Because when you're listen, if you want to find something that agrees with your opinion or what you think on the internet, you search long enough, you can probably find it. But at least according to the Googles, Ampere uncertainty. Okay. Oh, and of course it doesn't even come up here. But as we can see, it basically ripped this from Wikipedia. So techniques to us. Oh my God, I'm sharing the wrong thing. I apologize. Hold on, that was on screen. We need to do a window for this one. Okay. There we go. All right, so the Ampere. All right. At least according to Wikipedia, take it for what it's worth. Just the initial general thing that I stole from Google is techniques to establish the realization of an Ampere at a relative uncertainty of approximately a few parts in 10 to the 7. 10 to the 7? That seems familiar from different things. Because if we inverted that, we would get 10 to the minus 7. Why is that important at all? Well, we go back. The Ampere's constant. What do we got? It's literally defined on Wolfram Alpha. That K there, that's just, it tells you right there. It's Coulomb's constant. So that's basically the constant of charge proportionality. What the heck is that? It's essentially, at least for the force equation, the same as the Newtonian. Hold on. The Newtonian one, which is... give me just a moment. I'm totally not... There, now we can erase the board. This is why it's important to document stuff. Okay. So all we really need right now is... Alright, you probably see the whole Newtonian thing, which is the gravitational constant of proportionality. What is that? That's that big G thing. Alright, so you got your big G over here. And you'll have like your mass 1. You'll have your mass 2. You multiply those together. You divide it by the distance or the radius between them squared, that R squared law. And basically you're going to get the gravitational force of attraction. All right. So the question is, well, what the heck is the Coulomb? Well, the Coulomb's constant, which they're using K. I like big C just because it's gravity. Coulomb. It's also in there. But if you take charge and charge representation, they typically use Q within physics. You see like Q1, you see like Q2, and then you multiply these things together, and what ends up happening is if you put your R squared, that's going to give you the force there. So basically, it's the proportionality of charge, kind of like gravity is to them. That's why folks are like, well, gravity and electricity are the same thing. You'll see graviton-electric papers and stuff out there. I don't know. Maybe that's the great mystery. But then again, it'll probably help to find out what the heck charge and gravity actually are. I mean, that would probably be useful along the way to figuring out what's going on and seeing what's going on between them. But that's not what we're here to try to figure out today. No. Today, we're going to raise maybe a wee bit of uncertainty. What am I talking about? Okay. Because, all right, so we just went over that Coulomb constant. I just use big C for that. That's just my personal preference there. Just to highlight the point that it's basically a proportionality constant between masses for gravity, kind of like the Coulomb's constant is the proportionality factor between charges, kind of using like the same layout here. Okay. But in order to get Ampere's constant, it's that Coulomb constant. It's divided by the speed of light squared. Oh, that seems to pop up all over the place. Cool. And this is like 1 over 4 pi magnetic constants, because if you take that and I think it is. I could be wrong. Could be over 8 pi. What is it? Okay, so 1 over 4 pi. That's just how it comes out related to other things. So, and again, it's not that I know this. It's just because Wolfram Alpha tells me so. Okay. Go back here. All right. So the Ampere's constant itself. What's this? We got 10 to the minus 7 Newton, which is the unit of force. All right. So we've got our unit of force per ampere squared. Okay. And it is literally defined as 10 to the minus 7 precisely. That's incredibly convenient. I mean, heck, there was a good period of time where we thought the speed of light was precisely 3 times 10 to the 8 meters per second. It'd be like 2.9978 or something like that times 10 to the 8. It was close. Not quite that 3.0 cigar. So, just hypothetically, what if it wasn't exactly 10 to the minus 7? What if it was almost? Because, I mean, to be fair, I mean, if you are at, like, I don't know, 10 to the minus 8, you're going to have, like, 6 9s and then a 2 in there. It's going to be, like, 0.99999929999 or something like that. That's going to look like 10 to the 7, isn't it? So that's why just the cursory search that we did over here is, so it seems to have a confirmed to about 7 decimal places. Okay. If it happened to be a little different, might that lead to something? Because you can actually see here, here's the conventional value from CoData. Because it says 90. There were a bunch of these constants that back in the day, they just set to like, it was in 1990, and they just said, okay, we're going to define these constants as this. So it like wasn't necessarily an official SI thing to my knowledge. It was just like, I think a whole bunch of folks were like, all right, we're going to define this. As you can see, you've got, okay, so the Ampere 9, as you can see, was defined as exact, and you have a deviation here. It looks like it's 1. I realize this is a different thing than the Ampere constant itself. I'm just highlighting this because one would think there would be a connection between the Ampere and the Ampere's constant, right? So as you can see here, we got our 1. We got 1, 2, 3, 4, 5, 6, 7. And then over here on the 8th digit over here, seems to be not Seems to have a wee bit of a deviation there. Okay. So let's actually just go to the Ampere from Wikipedia. All right. Again, take it for what it's worth. That's the best way to maximize that. Okay. So, all right. Oh, welcome, friends. I'm sorry. I need to get back to it. Sorry, I had to adjust the audio, do all the different stuff and things. Yes. Yes, Rick. Amplify it. Is that where it came from? No, I think that's ampli, not ampere. Uh-oh. Uh-oh, nerdy. The mystery is the mystery generation. The universe's way of creating. I have no idea. We'll see. We'll see. Oh, we're getting to that. We're getting to, because that was one of the things where when you're reviewing the history, and this is one of the things I came off. I think Rick actually brought this to my attention. Is you look at some of these things and it's like, all right, we believe it's this. And to be fair, Ohm's law, that's the empirical law. Because they call it empirical because apparently they don't believe there's an actual combination. It just seems to be an observed thing that, it seems to be about this amount. And again, I will confuse things here just because I'm saying when I initially planned this stream, I had it defined. I was off by like 18 orders of magnitude. I took elementary charge and I divided by 1 second. And I realized, wait a second, no, that's like 10 to the minus 19 amperes. It's actually 1 coulomb divided by 1 second. Okay, is defined as the ampere. Okay. 10 to the minus 7 memes per second. Oh, God help us all. Okay, well, looks like I'm not gonna lie. Isn't that just like the spring thing? It's kind of like for the spring constant. Again, it's severely lacking in traditional education on these things. Most of it's just like, all right, how do these blocks fit together? Try to wind up some other things there and see what we can't figure out. Oh, it was about 95% dark memes. I thought that was Twitter. I could be wrong though, but I digress. Let's go to our friends at Wikipedia for a real quick overview of what the heck an ampere might be. All right. So the ampere, nothing. That's capital A here. Sometimes you'd hear amp, like the number of amps, and people always say it's like, be careful of electricity. It's not the volts. Nikola Tesla had like millions of volts going through him or on his surface or something like that. It's the amperes that will get you. But to be fair, when you just go into the equation, it's like, well, there's going to be some sort of mass or something moving along, and who knew? All right. So basically, André Maria Ampere is often credited with Hans Christian Ørsted about the whole what is going on. So as you can see, it's equal to 1 coulomb of charge moving past a point per second. So it's literally should be. Oh no, I went the other way. Should just be coulombs, divided by second. Now give us the ampere. We got our ampere here. And Wolfram math is nice, and for those of us that occasionally pay attention to different things, that 2.998, it looks to be the beginning digits of the speed of light. Now, as we can see, we have our stata amperes here. We have our ISUs. But it's not the correct power. It's off by a factor of 10, or at least for the speed of light, because again, this isn't in meters per second. This whole dimension is literally current. I think that's kind of cool. It just shows you these relationships. I had no idea an ISU or an EMU or things and stuff. Those were just depreciated terms that we don't really use anymore. Okay. America also runs on Duncan, by the way. All right. So as of the 2019 redefinition of the SI, the ampere is defined by fixing the elementary charge, so basically the charge of an electron or a proton, to be basically this number, that 1.6 times 10 to the minus 19 coulombs. Okay. Which means an ampere is an electrical current equivalent to 10 to the 19 elementary charges moving every 1.6 seconds, or approximately 6 point. Okay, that's kind of weird saying it that way. Although breaking it out and just kind of having the exponential power there kind of reminds me of that's logarithmic calculation for closed forms for the Planck constant. So that's kind of cool. All right. So basically, we're approximately blah blah blah. That many elementary charges moving in a. Is that right? Hold on. Yeah, okay. 6.242 times 10 to the 18 electrons per second. Okay. I'm just like, wait, hold on. It's again, trust but verify again. It is Wikipedia, and again, just because it's on the internet, just because it's on Wikipedia, heck, just because it's in a paper, doesn't mean it's right. Could be. But as we can see, so prior to the redefinition, this is the crazy thing, because this was like the original definition. Went away for like 60 years as people were using like different like cathodes and anodes and detecting how much mass of silver ends up being collected and stuff like that. Long story short is they literally went back to the original definition. So the ampere was defined as the current moving past two parallel wires, assuming they're in a vacuum and they would go up to infinity, yada yada. Invoke your spherical cow that doesn't actually exist there, just to make it easy, because well, the physicists aren't mathematicians always. So, so 1 meter apart, that produces a magnetic force of 2 times 10 to the minus 7 newtons per meter. Okay. So there are very interesting ways to define these things. So basically, long story short is this is, where is this? Good, like right here. Okay, so again, Wolfram alpha has the same thing over here, and it actually has the conversion factor. So that's the magnetic constant here. That's the amount of current, big I squared, and then divided by 2 pi, and then d would be the distance. So that would be 1 meter apart. So if we, let me just do it over here. I'll bring it over. All right. So that would be, so that's magnetic constant, current squared. We're doing 1 ampere. All right, so we'll do magnetic constant, ampere squared. And we're dividing by, was it 2 pi, and then the distance is 1 meter. I think that should do it. There we go. Wait a the force per meter. Okay. All right. So Nolan was right. Okay. So force divided by length. So, okay. So this generates the force. That's the force. And then the length, we're doing 2 pi and the distance, because I'm going to assume some form of sinusoidal thing. Okay. So that gives us, that's the force. The interesting thing is when we do that, let me just make sure I had that right. 2 pi and the distance. Yeah. Okay. So that's saying the force, that 2 times 10 to the negative 7. The interesting thing is the dimension that comes out is the spring constant. Or a force gradient, which is interesting, which maybe sounds... It's all the way from Peel strength, Graves tear strength, spectral radiant energy density with respect to wave number. Well, I think that's probably where that 2 pi comes from, because waving. Or it's also clavage, because, well, mass divided by time squared. Okay. So that's interesting. All right, so if we just want just the force not between a distance, an Ampere magnetic constant divided by Ampere squared is, oh look, it's I think that's 4 pi times 10 to the negative 7 newtons. Oh no, is it? Oh yeah, well this is like a 4 pi thing because you see this here if you moved. Hold on, it's gonna be like 4 pi divided by 10. Or 2 pi divided by 5. There you go. Oh, that's interesting. I never even thought of that. 4 pi. Yeah. It's just because if you move this decimal point over, it's... See, you spend enough time going down Wolfram holes, just series of numbers look familiar. It's like, oh, hey, look. Oh, there's my friend. It's a sphere. Don't you know? All right. I should probably get into why I'm talking about all this. All right. So now that we've rambled on for about 20 minutes or so, what is a force gradient? That's a great question. I'm going to assume it's some proportionality of force that's going to change over some distance there. I mean, that's just kind of how I always just kind of like view charge or something like that. It's like, I don't know, I played with magnets before when I was a kid. It's like, oh, you're going this way. All right, if you're going to have some charge, basically, as far as we know, there's no magnetic monopoles or anything. You only have charge monopoles like a proton and electron, which seem to be emit like spherical charge stuff. So if you get a proton and electron, or if you have two protons, basically your two magnetic things or whatever, you're trying to push them together. I'm like, all right, you're gonna feel a little bit of force. As you get closer, it's gonna be a greater force, and that's why at the bottom, if you set the distance and then you're dividing by a wavelength, that's why I assume we get that amount. But it is interesting in that, what does it say? Now, did it actually say force? Force? Oh, force per meter. Ah, okay. So that's not the actual force, that's the force per meter. Okay. That is interesting. Oh, because we take out that and we just have our 2 pi then. Okay, there we go. There we go. All right, so we took out the distance and then we did our little rotation there. There we go. 2 to the 7 newtons. That's what you get. And then if you do that by a meter, that would be a meter. Okay. That's interesting. Wait a second. So there, the force between a meter there, and then, but if you just put 1 meter in, it doesn't change it. It just changes the dimensional output. It goes from force, which is mass times the distance, and that's divided by an acceleration. Because force is mass times acceleration. Acceleration is a distance divided by time squared. Because a distance divided by a time, it's going to be speed. But if you're accelerating, you're going that speed per unit of time. So you are accelerating. So as soon as you multiply it by meters, you get mass. Excuse me, you're dividing it by the distance. So when you divide it by that, you're taking out your unit of length and just converting it over to that spring constant. Oh. Huh. Okay, so I'm learning things, so thank you all. Yes, yeah, hypersphere, yes. 2 pi squared times whatever our volume is or whatever, and then you multiply. I don't know. That's part of the conversion. All I know is different topics. So let's actually get to what we're supposed to be talking about. So, all right. So again, this was inspired by Gareth from where are we? Which one was this? This guy. Sorry. No, that's not the right one. Hold on. Here we go. All right. So this is Gareth's video. is from See the Pattern. The link is in the doobly-doo below. Let me just bring those up. Crop tab, See the Pattern. All right, so let's watch. See, okay. First off, this is totally where I stole my thumbnail from. Thank you, Gareth. Greater than the doobly-doo below. All right, let's actually make this to better bit rate and everything. All right. So let's see what we got.
Take 2 bar magnets, place them side by side with like poles facing, they repel. That's basic magnetism. Now, take 2 coils of wire, run the same current through both in the same direction. Each coil should act like a bar magnet. So, what do you think?
Oh, hey, Courtney. I was just talking about electricity and the magic thereof that we still don't really know how it works. I believe it was our scholars from the Insane Clown Posse that said, was it something soil, earth, fire, air, water, and dirt, frickin' magnets. How do they work? Sean Carroll brought that to my attention. He's actual physics professor, but the general sentiment, it's like, oh yeah, of course. No, this end goes this way, this end goes this way. We break it in half, and well, it just seems to keep doing the same thing, but breaking into 2 additional magnets. Why? Something, alignment, charge, and this and everything, but ultimately there are still electromagnetic effects that people are, I don't know. How does it work at the most fundamental aspects? Don't know. It's fun to ponder about, and I'm thinking we can figure it out. To be fair, there is a lot of stuff that we know, and heck, I'm discovering things that I didn't even know like 10 minutes ago, and it's like, oh, that's interesting. I'm a noob. But, yes. Oh, don't worry, we're not going to be talking about ICP as much here, but we're just going to watch this little thing where this is something that I like, Gareth, because some folks go out there and they'll say the very over-the-top thing. It's like, he'll say things like, he'll ask a question, like, well, here's something that people aren't really talking about that maybe isn't important that people have kind of not talked about for a while. So let's watch this a little bit.
Think will happen? They should repel too, right? They don't. They attract. It's not what you'd expect. And it's not something most textbooks ever mention. But 200 years ago...
So, what is going on here? All right. So basically, the whole concept of, all right, so you got your charge, you got your north, you got your south, yada yada, it's spinning around there. Now, normally if you have like 2 straight wires, and if it's the same type of charge going in the same direction, normally they repel. Why, if you turn it into a little coil in a loop, does it magically seem to start to attract? Veritasum actually did, I think, a pretty good video on this about if you flip a light switch, how soon will the light on the other end go? Is it like, I don't know, like 137th the speed of light? Because at least what I was taught initially, or at least had heard, was, well, oh, no, electricity, oh, that thing that's turning the... That's just a whole bunch of electrons vibrating around going through a wire. I'm like, all right, that makes sense to me. And then you realize the light's essentially going to start getting its energy and turning on at about the speed of light. You're like, wait, but the electrons don't actually go at the speed of light. Like, it's going through the wire. It's going fast. It's not going at the speed of light, though. At least as far as we know. And it's like, wait a second. It's just that whole oscillation. It's causing like the electromagnetic field to do its thing. And you're like, oh my god, engineers are wizards. I don't know. We're going to get to the other video where Dr. Aziz, he translated a lot of this. They're talking about Ampere's forgotten law. Why are some of these things forgotten? Well, maybe somebody mentions it, but you're like, we just go back. It's the days of the internet. We just go and we read the original works. And you're like, cool. Except apparently until Dr. Aziz actually translated Ampere's works, the original works were just still in French. Now, if you could speak French, cool. I don't speak French. I'm sorry. But so basically, this is literally something within like the past 5 years. I think he translated it during the pandemic or something. It's like there's hundreds of pages of like letters in some of his papers that he translated through. Now they are available for free. Some of the links in the doobly-doo there. If anybody wants to check it out and figure out what's going on from some of the OGs themselves. So let's continue on this a little bit, and we'll get to a point. I swear.
And it's not something most textbooks ever mention. But 200 years ago, André-Marie Ampere uncovered this exact behavior. He didn't just observe it, he built a theory to explain it. A law that treated electric currents as real physical entities interacting directly with one another. Not through fields, but through force. And his experiments were so precise, so compelling, that James Clerk Maxwell later called Ampere's discovery one of the most brilliant achievements in science.
So, for those of us that, like myself, that aren't up on so much history of science and physics, James Clerk oh my god, I don't think I've ever seen that picture of him with that beard before. It's quite impressive. But James Clerk Maxwell has brought us the Maxwell equations. What are those things? The things that basically say, like, how electromagnetism works, and basically calculate and estimate the speed of light to a pretty good proportionality based upon the measurements and stuff. Yeah, one of the most influential. Some folks would say that the Maxwell equations may be the most impactful equations of all time. And again, that's up to your interpretation, what you value on. But I'm just saying the only reason any of this stuff works, that anybody's able to remote view what the heck some masshole in Massachusetts is rambling on about right now, is electricity. Thank you. Let's go on a little bit. So,
A law proven by experiment, not to be ignored. And yet, that's exactly what we did. Ampere's law wasn't just a curiosity. It posed a challenge to the very foundations of how we think about electricity, magnetism, and the fabric of space itself.
okay, so we're just getting into that. So we're half an hour and let's actually get to a point. Okay. So, I gotta go back to the window mode. Window mode. Here we go. All right. So, let's go over here. All right. And shouldn't use all these thingies in the same tab. All right. So as we can see here, bada bada boom, the ampere was defined as the current passing through two parallel wires 1 meter apart with our force of our 2 to the minus 7 newtons per meter. And when you divide a newton per meter, which is, the newton is defined as, you can see up there, 1 kilogram times 1 meter divided by second squared. Okay. So mass times acceleration, the kilogram is the mass. That m divided by the s there, that's just like 1 meter, so like 1 pirate length step divided by second squared, because it needs to accelerate, kind of like you're in a car, you're accelerating, you're going faster and faster and faster. All right. Within the legal limits, again, modern internet, just saying. But basically when you divide that by 1 meter, you get rid of that whole, that meter term. You divide that meter by another meter, it goes away. So it just goes a unit of kilogram, so a unit of mass, divide by second squared. So like as Nolan was saying, that's where we got that that spring constant thingy. We're like, wait a second, how the heck do we justify this? But this is just how it's defined. I'm counting on a lot of this stuff works extremely well, because this is also how I justify any of my calculations and pretty much other papers and stuff like that I actually will finish. God, need to actually finish them. You can stop half-assing things, so pardon my French. All right. Again, I don't speak French, but God, bad at attributing. All right, so here's the crazy part: is hold on. Hold on. Should I go to my paper? Because this is kind of how they defined it before. You're just putting in like silver nitrate solution, drawing it out. Okay. Let me just search for the uncertainty. All right. So where is this? The former definition of SI. Okay, so this was the old definition, and we're upgrading to the new definition. So the Ampere's force law. Okay. See, we've got our things. We got the little circular things. That must be that 2π term that I was in there. And again, listen. People make a big deal about like the AI agents, the chat GPTs, the DeepSeeks, the Groks, the whatever it is. Some folks, it's very interesting. Side tangent for one moment. Okay, so the side tangent for one moment is people have some very strong opinions about AI. It's very interesting. Some folks are like, I think a lot of us are like, oh, that's kind of cool. It seems kind of novel. Seems to be maybe a little bit weird, but all right, some new stuff out there. Some folks are either like, the AI singularity is coming. Fear our AI overlords and stuff like that. And they're extremely confident. And you all have some other folks that are like, this is like the biggest nothing burger since, I don't know, the iOmega zip drive or something like that. God, I'm old. If anybody gets that iOmega zip drive reference, it's okay. It's okay. I feel you. Time is a thing that's just going to keep flowing as far as I know. But again, people are very confident. And I look at some of the folks that have differing opinions. I'm like, oh, that person's really smart, knows a lot more than me. That person's really smart, knows a lot more than me. I'm like, it seems almost like a religious argument. It's like, it's literally, we have faith that we are correct. We know we are correct. Do they actually know? Or is it more of a held belief? I don't know. Hey, people are all open to their opinion. All right. Back to our originally scheduled pretending to be a science dude on the internet. Yes. Nerdy is one of the OG rodents and digital pickles I met on the internet. That is for those with the real deep lore. God. If I ever get roasted for my 15 minutes on the internet, God, people are gonna have a heck of a time. It's like, he had this digital pickle on his channel and stuff. The lewdness, the disturbing nature, the controversy from the old videos. I'm too lazy to take most of those down. If something is terribly hurtful for some reason, people, hey, they can message me. I've taken things down, or at least pull them publicly, just because, hey, somebody asked nicely. Try to be respectful. Hey, welcome, David. Yes, I make it. Okay, to clarify, so at some point in the 90s, we had CDs. CD burners and stuff were becoming a thing, but it could take an hour or so to burn a CD. It could take a while. There could be errors and stuff. But a disc printed pretty fast. So a CD at the time was, I think, like 500 to 600 megabytes. The iOmega zip drive was supposed to be 180, which could actually get a lot of files, not as much as a CD. But the whole claim was you should be able to burn it a heck of a lot faster than like a CD. It's like, okay. Ultimately, I don't think it worked as well as people thought, and CD technology got a heck of a lot better. And yeah, it just kind of went away. And a lot of people invested, I guess, and yeah, I think it was one of those things like $60 a share down to like pennies, and the company got parted out. I might just be making that up. It's been a while. Oh, nerdy is saying some words. It's almost as if people have been working with AI since the 1950s. Now, where did I put my Winchester drive? There's a lot of things that are within the general public discourse and consciousness, so to speak. There's also the quote-unquote undercurrents, pun included, of the discussions of either that particular time or maybe if you were there. Because the interesting thing is, when you talk to people that were there, like you'll hear like this discussion of history and stuff, and then you start to talk to people that were actually there, like a Stephen Wolfram or something, where it's like, he's in his 60s now, so he did have a chance to actually meet a lot of people that were quite big within the physics community of like the 20th century, because he worked with Professor Dick Feynman for a while. And oh god, I would have loved to be a fly on the wall for like a young Stephen Wolf from a 60-year-old Dick Feynman. It's like the ultimate odd couple. It's like Stephen Wolfram, young, proper British chap, and then 60-year-old, wild-haired Dick Feynman. That's it's like an over-the-top, brash New Yorker type personality, and just it's. But they both love physics, and apparently they had different games where it's like, all right, we need to seek out the fatal flaw in somebody's argument, so we can kind of like just pull out that block and see if their entire argument unravels. Now, if it's true, maybe there's something there. But we continue on. Hey, no. Don't let that fool you. It's just the technology. I'm just a lame language model, Courtney. I just kind of fill in the blank. So that's also interesting. You hear other different folks as well, and Rick has been in some interesting situations, and you talk to different folks, and folks, just because somebody doesn't say something, sometimes I claim silence can speak volumes. All right, so let's actually get to a point now. After, all right. So apparently, this is one of the things I learned in my unit project is that whole kibble balance. What the heck is that crazy thing? It's like, all right. So basically, you take a mass, you put a mass there, and be like, all right. So we know this thing's mass. We calculate the other factors, and it's basically using electromagnetism and charge to help balance it out. So you can see the relationship between mass, charge. Well, technically, you're going to be running current through there to help maintain that charge and everything. So basically, as we get really, really good instruments, and we can probe deeper and deeper into fundamental stuff and things that are going on within reality, we should better measure these things. And so let's be fair here. So now the definition of the Ampere was most accurately realized using the Kibble balance. Okay. But in practice, the unit was maintained via Ohm's law. What is Ohm's law? So it just says via the pop-up there that the electric current through a conductor between 2 points is directly proportional to the voltage across 2 points, introducing the constant of pressure, blah, blah. Okay, so let's actually go to NIST's definition. It's far, I don't know, it just makes it easier for me. Where is this? Pair. What did I do wrong? I can't spell empirical, can I? Wow. It's not on this page. It's on, where did I put that? Let's go back to that page. I think it's in the history. Here we go. Oh, no, it's not. Oh, my God. It's okay. Fine. It's the present. Or it's either that. No, it's the next one. The quantum meteorology triangle. Here we go. Okay. God. Terrible presenter. Oh, hold on. Oh, that's why. I have my brow. Talk about noobs. It takes you 10 years of using a Mac to realize, wait a second, I can just zoom in on these things by Command Plus. So dumb. Okay. Here we go. Empirical. Boom. Oh my God. Why is it not? Is it just on the Ampere itself? Oh, I thought I was, okay. Wow. I'm like blowing my mind right now. Oh, I can't spell empirical. Hold on. Okay. Wow. I could have sworn it was at the present. Okay, here we go. All right, after making myself look like a fool for the past 60 seconds. God. Here we go. So we can see here, but there's a catch. Ohm's law doesn't quite, and this is from NIST, the National Institutes for Science and Technology. As far as I know, at their Boulder, Colorado office, they have some of the finest metrology equipment. Shout out to Bill, was a metrologist, basically in the world. All right. So as we go back down here, let's as we can see here, Ohm's law. Can I make this a little bit bigger? Let's see. No, that's too big. All right. So Ohm's law doesn't quite have the footing of, say, Newton's laws of motion. That is, I, which is electrical current, is equal to V, which is volts, divided by R, which is the resistance of the material. Can't be deduced from other laws of physics. Instead, it represents the seemingly unvarying relationship among the three electrical quantities as measured by various techniques around the world. During the past 2 centuries, that sort of formula is called an empirical law because it is based entirely on observational evidence. Okay, so to date, it appears that Ohm's law successfully describes measurement made with uncertainties in the range of parts per 10 million. According to one report, still holds in nanowires 1 atom tall and 4 atoms wide. Okay. So that is one report. That may totally be the case. Okay. So why am I putting this? Okay. It's accurate to parts in 1 in 10 million. What is 1 in 10 million? Oh, we got our friends at Wolfram Alpha. 1 over. Okay, so 3 zeros is 1,000. 2, another 3 is 1,000,000. And then 1 more is 10 million. Oh. So it seems to have an accuracy of about 10 to the minus 7. That's interesting. Okay. Hypothetically. Now, again, if we happen to have accuracy to about parts 10 to the 7, okay, and if our Ampere constant, excuse me, oh, actually, let's just multiply by the Ampere. Or just put the Ampere there, Ampere. Oh, all right. Okay, so it has 10 to the minus 7 for the Ampere, all right, because that's coulombs divided by seconds, all right. Okay. But wait a second. If it's got that, but the Ampere's constant, I'm just going Ampere constant, is literally defined by a 1 that's 10 million over there because, yeah. Now, again, I might just be blowing this up out of proportion. Maybe I've just been completely brainwashed. I don't know. Maybe the Physics Monastery is just a cult and everything. Maybe just a whole bunch of random crazy people just flinging random stuff against the wall, and there's no there. However, if on the off chance that perhaps, hypothetically, of course, there was a wee bit of there. That was a lot of theirs. Might something interesting be going on at that 7th decimal place? Or the 7th significant digit, so to speak. Because, okay, if we've got accuracy to about... Now, to be fair, maybe they're talking about past this. So, Let's do. Let's actually just do that. Okay. So it's basically the main argument here is if right now we basically have an uncertainty about 10 to the 7, and the magnitude of the constant of that unit has a magnitude of 10 to the minus 7. What if there happens to be a really small discrepancy? I mean, I'm just saying that maybe, I don't know, Mr. Ampere. Oh, hold on. Codata. Okay. So they might not even have the Ampere in here. Hold on, let me search for Ampere. Okay, so they actually don't have the SI unit of the Ampere. They only had the conventional value of the Ampere as it was defined in 1990. So, symbol for the equation. So, basically, this is based upon, that's the Josephson constant, the von Klitzing constant in 1990, and then, it's multiplied by the Ampere itself, which is interesting. Okay. As we can see here, we get about 7 digits. And it's not precisely. It seems to be something a little... Actually, let's just grab this for a second. I'm just curious. I haven't even done this. See what happens if we... All right. No, we just need the inverse of that. Okay, so the inverse of that, apparently, gives you 1, 2, 3, 4, 5, 6, 7 in this form, and then, right around the 8th digit there. Okay, it seems to be a little bit of something different, so hypothetically, if around the 7 decimal place, which coincidentally for most of the Planck constants is the kind of limit of our knowledge, and again, most of that is due to uncertainty in Newtonian gravitational constant, big G, because that's basically how they're defined, but it's very interesting that I think it's attributed to Lord Kelvin or whoever it was, that the future of physics is seeking the future of physics is in seeking the 6th decimal point and beyond. I used to kind of make fun of that statement a little bit, and then I think I heard it actually quoted correctly, and that the actual future of physics was there, because if you want to give credit to somebody, it's like, the future of physics lies in the 6th decimal point and beyond. Okay. Coincidentally, right when we got to around the 7th decimal place, things seem to kind of start getting wacky, and I guess we really need to start quantizing things and doing all this weird stuff. What is the actual claim? We're going on an hour of me rambling on charge and constants and being confused and trying to learn things. What the heck is the point? Hypothetically, if Ohm's law, which, again, I'm saying Ohm's, but it is relating current and everything. So maybe I should add this to the decimal point. Where are we? Present. Okay. So this whole current equals voltage times resistance. Okay. So voltage times resistance should give you current. Okay. This is what we seem to observe. It seems to be the case. Ultimately, what if it was kind of like the speed of light, and it looks like it's just going to be an integer number times some power, which right now that's literally what's defined, the integer of 1 times 10 to the minus 7, 1 in 10 million, which seems to be about the magnitude where the uncertainty we've measured to. Hey, maybe we'll keep on measuring it. It'll be totally fine. It's 10 to the minus 7. The sheer fact that if that is the case, that is freaking interesting. Why the heck should our units come out this way? That's a question in and of itself. hypothetically, what might actually happen, because Ampere's constant is actually defining magnetic permeability. So the permeability of, well, that'd actually be the magnetic constant. Because the magnetic these constants are looped together by like pi, 4 pi, c squared. Because if you just do this, you go, here's a Wolfram hole for you. You take that constant, we go to c squared, we're going to get Coulomb's constant. Okay, it says that. Cool. So then you got a Coulomb's constant. How does this relate? You're looking at this, you're like, why does that number look familiar? Let's do 1 over Coulomb's constant. Okay. So we're getting those numbers there. What the heck does that even... Hold on, let's show you some. Why is it not showing? Oh, it's... long story short is, this is basically the speed of light squared numbers. Oh, well, that's obvious why that's the case then, because if you divide it by the speed of light squared, it's going to go down to, all right, so yeah. Or 10 to the minus that, because c squared is at 8 point unit. C squared is at 8.988 thing, because it's, well, speed of light by itself unit. It's 2.998, so you square the thing, bada boom, bada bing. It's just under 3. If you square 3 times 3 is 9. It's a wee bit under 3, so it ends up being a wee bit under 9. I mean, that's just the logic I just go through. It's yeah, again, it's, I don't have all the training and stuff that I should be. I have no idea if that's useful or not. I feel like I'm at an extreme disadvantage. And the only thing I'm relying on is the guardrails and the computational power of Wolfram Alpha and the vast majority of human knowledge that is mostly free on the internet. Yes. Hey, K-Show. Good to see you. We're just talking about a little bit of current and maybe how there may be a little bit of a kink, so to speak, in current. Why? Because this whole Ampere constant. Let's go back to the dang thing here. Let's go back. You got this thing here. So I typed the magic words Ampere constant into Wolfram Alpha. Okay. We typed some words. It gives us this little definition here. It tells us the values in all these different units. You can get step-by-step solutions on how to calculate all these things because, well, that's what it does. Okay. So the unit dimensions. These are the dimensional ingredients that make this thing up. So you're like, all right. So this is a mass times a length. All right. So you got something with some mass. It's going to go like a distance. All right, cool. And that's all. See, these are positive. This would be effectively to the first power. If it's to the first power, it just means it's in the numerator. These negative exponents at -2 and -2, that just means it goes in the basement below. So it's basically time squared and current squared. So it's a mass times a length divided by time, current, both of them all squared. Okay. That's confusing to me, and I'm sure I'm the only person that's ever been confused by units in the history of reality. Thankfully, smarter people than myself, thank you, Thad, pointed out that you could just do it something like this. You could just be like, all right, well, it's a mass, kilograms, times the distance, meters. All right. And then, what is time current? Let's get to that first. Second, Ampere. For those of you that have taken some physics and been perhaps following these videos, you get an Ampere second, which, oh, look, it's 1 Coulomb. Because if we go all the way back to the beginning, if we take 1 Coulomb and we divide it by 1 second, That's how we get the ampere itself. So you could have your time squared and your current squared, but that's just going to be Coulomb squared. That's going to be charge squared. Okay. I'm getting into this for a reason, just because the rabbit hole or Wolfram hole it goes down, so to speak, is so fantastic. It took me about an hour to get to a point, but let's get to the actual fun part of this, and how this may actually reveal interesting things that may help move science forward, I claim. All right. Before that, let me just caffeinate up. Let's play a little word from our sponsor. Let's see, where are we? Let's play the... Did we already play? Oh, yeah, we already played the Hacking the Universe on a MacBook Air. Where's a good Wolfram thing?
World exists on the top of a giant turtle.
I can neither confirm nor deny that.
You finally flipped.
Yes, finally flipped. All right, where are we? Ah, yes. Let's get to the point. All right. So why does this matter? Okay. So the interesting thing, and this was brought to my attention by Thad, and again, maybe it's nothing, but coincidentally, that 7th significant digit seems to be where we kind of really needed to start to quantize things, so to speak, in a quantum physics type of way, and we learned a whole bunch of things, and there seems to be all these crazy, weird phenomena that don't seem to make sense. There might be an asterisk there if it's computationally irreducible, and there is something to Professor Barandas's individual stochastic process, which I'm gonna clip the video from that because it's now publicly available in the Wolfram Institute. That it's a fascinating thing that stuck with me. I'm gonna see if it would be great if the two of those folks get together and have a conversation. I think it would be very productive, in my opinion. Okay. So why am I showing you this? Because if we go back, okay, our meters. So rather than doing that whole thingy here, so this is just the ampere constant. So that ampere, that coulombs divided by seconds, this is its constant. Okay. A mass, a length, and we could computationally reduce this to charge squared. So let's do that. All right. So we're going to do that, and then we're just going to divide it by coulombs squared. Cool. Okay. So, well, doesn't that kind of look like the acceleration of gravity or something like that? It's I don't know. I don't know enough. What is the acceleration of gravity? It's like about 9.8 meters per second, but that's ohms per second. Those are completely different units. What is it? Earth gravity. 9.80665. 9.806. What the heck is going on here? Okay, this... Okay. Pause for a second. I'm not gonna lie, I have no idea what's going on right now. No, that's... the gravity on there. I mean, this just has to... What the... Meters per second. Equivalently in newtons per kilogram. Standard gravity, 9.80665 meters per second. .80. is it? Okay, so the equator is a bit different. All right. 9.80. 9.80. 665. 665. I'm sure there's an obvious reason for this. So, I was hoping to explain things, and I just thoroughly confused the heck out of myself. Hold on. This is oh, it's because I expressed in kilogram force meters. Why did that happen? Is it just doing the voltage charge per game? Hold on. It's got to be related. I mean, this is just SI units. Why would it happen? Hold on. Divide by small g, Earth gravity. No. Standard acceleration due to gravity. Okay. So the difference between that kilogram force meters, the Coulomb constant squared, and the standard acceleration due to gravity on the surface of Earth seem to, and again, that's the average. The equator is larger, full disclosure. The average gravity on Earth with our SI units equals up 10 to the 7 Ampere constants. What the heck is going on? Because as far as I know, the gravitational acceleration on Earth, what the heck does that have to... Okay, I think my mind was just completely blown. Like, I saw like the first 2 digits. I'm like, that sounds about the same than usually have. Okay, why? Rick is commenting, Earth's gravity creates 1 atmospheric pressure at sea level. Wait a second. The atmosphere... Hold on. I think Thad has it. That's one of the things that I think Thad requires to actually calculate the constants of nature. It's like, I think it's either like 1 atmosphere or the freezing point of water on Earth. That's okay. I was not expecting that. Okay. Wow. So I'm happy I came back on today. It's had a little conversation. We talked with a little bit of discourse with some folks over the weekend, and yeah. I guess we just need to pay attention and engage in the scientific method. Because let's face it, hey, we all have our own biases. We all have our own ways we view the world, and some of them might be more useful than others. But perhaps sometimes, rather than just stating, well, this is obviously the way it is, perhaps a better thing would be to spend time and formulate the proper question. Because this is something that Thad had told me of. Apparently, Professor Einstein, long ago, it was said that he was proposed with, Professor Einstein, if the world is going to end in 1 hour and you need to solve a question, how would you go about solving it? And he said, I would spend 55 minutes formulating the appropriate question and 5 minutes solving it. Because if you're asking a question maybe it's a good question. Is it the question that you are trying to answer? Is it the question you're looking for, so to speak? Perhaps it is, perhaps it isn't. Because a lot of times, maybe this is just a human thing, but a general thing that I notice from a lot of internet discourse is a lot of times people talk past each other. You know, folks saying things. And then people add in, well, but this. Well, you didn't initially say that. And then somebody will say, well, but this. It's almost like you go from statements that you could try to logically evaluate to here's an epicycle, but here's this epicycle. And by that whole time, there's all this noise, people hate each other, chaos, blah, blah, blah. Discourse breaks down. I'm like, all right. What if, rather than just saying a whole bunch of words, what if we maybe spent a little bit of time, ask some perhaps extremely good questions, and those extremely good questions could perhaps lead to something quite interesting. This kind of took the wind out of my sails, I'm not gonna lie. I was gonna show something completely different, but I'm not even really sure what to think. I mean, if hold on, let me go back. What the heck am I even calculating here? What is a force meter? Hold on, what is it? Because I completely. Okay, yeah, all right, yeah. So we get that, and then if we just hold on, let me make sure we got that. I'm sorry, I have to look at it from this. Just do kilograms, meters. This should. Okay. It's just. I mean, I don't know what that is. Don't know what that is. All right. So it's a force meter. We just inserting force there. Hold on. Syntax matters. Or maybe it's. Oh, kg force meters. I think we're just. Is it kg meters? I think it's just literally. Okay, so if kg force meters is going to give you that there. All right, so maybe that's. Oh, that's the ratio. If you do that, you're going to get more digits. You're going to get the same thing that we had there. Okay. Also has to be the GZK limit for energy of a cosmic ray of 8 joules. I don't know what that is, but kilograms force meters. Kilogram force. Okay. Not in a named unit system. It's okay. Huh. I mean, this is just energy. This is the dimensions of energy. I mean, that was what I initially thought, but kilogram force meter. So, let's just do this. All right. So let's do kilograms. C squared. It's gonna give us a ginormous number. All right, yeah. So I got C squared in joules. All right. And then kilogram. I mean, these are the same dimensions. Mass, length. Mass, length. So if we divide that by... All right. Divided by meters? Should give us force. All right, so it's giving us newtons. what I need to divide it by. It's still really big. I need to get 16 orders of magnitude. Or go down 16 orders or 15 orders of magnitude. Okay, my mind needs to digest this. Wow, it's I was not expecting. Okay, maybe I had seen. All right, the force meter isn't. I see that once in a while, but I always end up. It always throws off my calculations. I'm like what? Well, what is that? Let's see. Rick is commenting, Daisy, Daisy, give me your answer due. I'm half crazy over the love of you. It won't be a stylish marriage. I can't afford the single carriage. You'll look sweet upon the seat of a bicycle built for two. Oh God. Oh, kilogram times 1 meter. All right. kg meter. Okay, yeah, that's it. Yeah, thank you. I can't get. That's just. It's mass distance. Mass distance. Because I've seen that. No, I've gotten those out for different like playing around with Planck units. Like, what is it, like big G? If you divide it by like c squared, you get like a mass distance divided by length divided by mass, but you can invert that into a mass divided by. Okay, there's some. Okay, but wait, no, Newton is mass times acceleration. Why does it? Wow. And every once in a while, there are things here. I've run across this before. You'll have. It's not in a named unit system. Okay, I'm gonna have to spend some more time pondering this outside of the stream. So, after completely having my mind erupt in some form of a internal supernova there, we've got a lot to think about. Yes, Hal 9000 is coming. Open the pod bay doors, Hal. That is an interesting comment, Nolan. Just considering, it's like Feynman's the claim that Nolan's saying that the Feynman's greatest quote would be, "What happens if you turn that off?" We have things as we know way that we know they are. It's like, all right, what happens if you turn it off? If I turn off the light, oh, you're just gonna see a little bit of the resonance here and everything there. You would suspect that. What happens if you were to turn something off and something weird were to happen? Something perhaps maybe unexpected. That really could help give us some new insights. Hey, Sean, good to see you. Sean's commenting, it's all about velocity. Well, I guess relativity would insinuate that yeah, it would depend on one's relative motion in regards to other things, because otherwise we'd be saying, oh, we could actually measure something, but rather than it being relatively, again, I am not a physicist by trade there. A lot of this is just language that I'm just either parroting or integrating into my lame language model mind about what might be going on. I just kind of have certain areas that's like, all right, somebody says, I can't do this. Why? There's a good reason. Cool. I'm happy to accept that. If it's not a satisfactory thing, kind of like it's... I was just going to point out, I'm like, how spectacular is it that literally we could have this guy? That we could have a constant. Literally, I could type in magic words in the Wolfram Alpha. And it comes out to be precisely 10 to the minus 7 newtons per ampere squared. I mean, 10, like literally 1 in 10 million. I mean, that's quite interesting right there. Pounds for, okay. Well, the thing is, usually I just view the pound as just whatever the conversion factor is, like 3.123 or something like that. The meter. It's again. I'm an American. Heck, I'm wearing a USA shirt right now. But my thing is, I went to a town hall a number of years ago. The first gentleman that came up asked a question. He asked that candidate, "Are you willing to lead America out of the Dark Ages and adopt the metric system or the SI unit system?" And the candidate was like, "I've never been asked that question before." And I sat back. I'm just like, it seems like a strange thing to ask. Start doing any type of calculations and working for something in any period of time, and you're like, probably not the worst idea. Again, I'm not saying you get rid of your standard 1/8 inch wrench or something like that. There's a transition period, yada yada, but yeah. All right, it's the weight of a kilogram mass. I think momentum time. Oh, momentum second. So that's. Oh, hold on. It's physical quantity. All right, yeah. Times seconds. Clarify. Oh, straight. Fine. Hold on. Hold on. Kilograms, meters, divide by seconds. It's momentum. Yeah, okay, that's the same thing. So, it's momentum time. Okay, you're right. Because if I put seconds in here, it's going to cancel out the seconds in the denominator. So it's going to be force meters. Okay, so it's momentum seconds. Mass distance. Okay, it has an interpretation here. See, that's the weird thing. Why does it have an interpretation here, but not here? Oh, do I need to? I mean, it's literally multiplying. It's going to give me a script again. Wow. Okay, I feel like I'm going to have to do a number 2 on this because I'm not sure why that should be the case. It's like these are supposed to be SI units that, at least as of now, are supposed to be based upon constants of nature. I mean, at that point, you would have to say something about the gravitational force of Earth is significant. I mean, how could that even be the case there? I mean, like, what would that even mean? Oh, geez, I think there might be some folks that are fans of the anthropocentric argument that I don't think I've ever heard that conversation before. Just because that seems remarkable to me. I was not expecting that. That was a question I wouldn't have asked if people weren't here. So thank you. I was going to go off into a whole other topic. Okay, I need to set up that units hypergraph that Dugan was suggesting. Okay, so long story, a little bit of back of the scenes stuff there. Let's hold on. Let me see. SI redefinition. Let's see if it's public. SI redefinition 2030. Allegedly, they are proposing to make the second the central unit that everything is essentially based off of. Okay, roadmap to redefinition of the second. This webpage collates some of the general and publicly made accessible information associated with the process. The time and frequency community is highly engaged in the long journey that will eventually lead to the redefinition second, possibly in 2030. Okay. So let's check up NIST. Did I miss it? Is this newer? Or did I just skip all the way past this? I may not have even researched. Wow. I'm so terrible. Let's see, 2030. All right, that was a 2018 read. Okay. Scientists will study the options and make a recommendation. If all goes planned, countries will vote on formal redefinition. Okay, so because basically, I think we're supposed to be getting something about being able to measure almost attosecond time, which is like 10 to the minus 18 seconds, which is basically, I think it's the thing we have the best way to probe, so to speak. Let's say I want to see if the chart is here, because there's a chart that I got sent. It's just I'm not sure how much stuff is actually public or whatever. Let's see images. I think that's the most recent one. It just looks a lot clean. Okay, it's not here. Why? Why? Okay. Why would you attempt to rebase most everything or use the second as your primary unit? Okay. Number one, I think we have the ability to probe it most greatly, and even with just the most current technology and definition, it's based upon second. It's based upon the oscillation frequency of cesium-133, or the hyperfine transition frequency of cesium-133. Blah, 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 blah. Hold on, let's go to data. Let's go to cesium. Because this is, hold on, no, that's the other one. Hold on, I'm gonna search for H bar. Because it's in here weird, because if you just search for cesium, you need like a dash in there. I think I found it by doing like 133. Frequency. Okay, here we go. Yeah, because it's abbreviated. It's not cesium. It abbreviates to CS-133. So, and okay. So long story short is speed of light we have to 9 significant digits. This we have 10 significant digits. Okay, even if you have a 10 significant digit of light, its first digit is a 3. This has a 9, so as far as H bar is defined now at 10 significant digits, it was 12, but the error was pretty large, so they just locked it off during the 2019 redefinition. So as far as I can tell, this is the constant of nature that has basically the largest magnitude of length of significant digits and just largest real number there, so to speak. Real, or hey, maybe we're just counting this as individual hertz. Maybe it is a non-negative integer. Who knows? Perhaps a natural number greater than 0, some may say. I like Easter eggs. What can I say? So if you're going to base it off of this, and if we have better clocks, I think there's some new thorium clocks that are going to be even better and stuff. Yeah, I mean, that's probably might not be a bad thing to base it on. And I'm curious if we could measure like another significant digit so of Ohm's law or Ampere's constant there, just to make sure it's precisely 10 to the minus 7. Maybe it is. Maybe it's a little different. If it is 10 to the negative 7, that's fantabulous. That's absolutely fantastic. I'm totally all right with that. I mean, heck, that actually made a lot of Thad's calculations easier before. But then again, if you tweaked it a little bit, it does actually seem to make some really good arguments or predictions. I don't know. I could go either way. I'm like, just follow the data, go where it is. Okay. Okay. So, well, we found some other interesting things for the 7th significant digit. I did not expect it to go that particular way. That was yeah, I was not expecting that. Guess we're gonna have to continue this tomorrow, where I go into perhaps a less exciting thing that It's probably not as significant, but just showing something interesting about the building blocks and actually, I know how we'll do this. We'll get into the significance of charge squared tomorrow. Use this as a bit of a primer, if you would. And again, feel free to conjecture ahead yourselves. Play around with Wolfram Alpha if you want. Again, it's a free website. Hey, use the LLMs if you're not really up on the math. Just spend time and try to ask the best questions you can. Because I think there's some real value there. And especially the sheer fact that you don't need to send letters between famous physicists, have access to all the journal articles, have somebody that can actually find all these things for you. You basically have the Library of Alexandria to whatever magnitude power now at our fingertips, mostly. Not all is still paywall stuff out there, but I'm going to try to... I have to be an optimist for a lot of things. I'm thinking that yes, we can. We can figure out what's going on to a much greater magnitude. Yes, I say that as I'm hand-waving, even though I'm not a big fan of hand-waving. Or, no, excuse me, no, finger-wagging. I hand-wave all the time. I do claim to be a very bad wizard, but that's okay. It's... David's coming, try to come to the market at 10mm sockets before it happens. Well, that's... I miss my Husky set. I did have a good Husky set. It was cool. Hey, add Earth to the coincidence. All right. One minor coinky-dink left. Hold on. I have to share this one little thing. Speaking of completely random numerology that I'm sure has no significance, we just took the kilogram, we squared it, and we happened to divide it by, I don't know, the Z boson mass. We get 6 times 10 to the 24 kilograms. I don't know what that means. That's approximately the magnitude of Earth. I'll leave you with that. Kilogram squared over the mass of the Z boson. It's about the magnitude of Earth. Again, I'm sure it's just a coinky-dink. But other than that, thank you all for joining. Peace out, everybody. It's a wacky and wild world out there, but it's hoping for a better tomorrow. One bit of science and maybe a bit of logic and maybe a wee bit of love in there at a time. So take care of yourselves, everyone. Peace out.